to be back here, and so I'm going to talk about extremal surfaces, decent entropy, and entanglement in ghost systems. This is mainly based on this paper, but also builds on this body of work in some with Dilip Jatkar, and this most recent one with Dilip and Kedar, and some earlier work. So this audience needs no introduction, but I just thought it would be good to put this anyway. So in the last 21 plus years since ADS-CFT, right? So we've seen that various examples of holography and so on of quantum gravity in some space-time region dual to some theory on gravity without gravity on the boundary. And it was probably Witten at strings 98 that said these in these words maybe, and which is that for negative lambda, negative cosmological constant, we have an asymptotically ADS space, and the asymptotic is a spatial infinity, and the dual is a unitary Lorentzian CFT, and it includes time. So time in the bulk is time in the boundary also. For flat space, which is lambda equal to 0, there's a null infinity structure that is natural, and this dovetails with the various studies of S matrices and their symmetries and so on that have been underway in the last few years. For positive lambda, this is de Sitter space, and this is fascinating for various reasons, but it's also less clear. The natural boundary here is a time-like infinity, either the future or the past, and so this is what I'm going to talk about in some more detail. And this picture basically is a picture of de Sitter, of global de Sitter. It's a sphere that's crunching and growing in time. The cross sections are spheres, and if you look at one line, then the upper patch or the lower patch can be thought of in terms of Poincare slices. With this metric, and if you look at both of these lines, then there's a static patch coordinatization that does this job, and I'll get to that later. So a version of DS-CFT or a version of gauge gravity duality for de Sitter space was formulated by Strominger and Witten long back, mainly by Strominger pushing it. And the statement is that that de Sitter space is dual to a Euclidean non-unitary CFT on the de Sitter boundary, which is at the future or the past, time-like infinity. Okay, and there's a lot of structure here that he explored and so on. A little later, Maldacena, in his well-known paper on non-Gaussianities, argued that this entire structure can be encoded as an analytic continuation from Euclidean ADS, and with this being the precise analytic continuation, which is the statement that if you start with this and you make these changes, then what you end up with is Euclidean ADS metric. Okay, and then you can use the Euclidean ADS dictionary, and this entire framework of inflationary perturbations could be encoded as a statement of this kind, with the precise statement being that the Hartle-Hawking wave function of the universe with regularity conditions at early times, this wave function is at late times, is equated to the partition function of a dual hypothetical CFT. Okay. So various things here work like analytic continuation, it turns out, but not everything, and so I'll tell you what works as analytic continuation. So in particular, for example, the interior regularity condition that we impose on fluctuations in Euclidean ADS amounts to a Bunch-Davies type initial condition in de Sitter at early times on the past horizon here, and so on. So in particular, if you look at a massless scalar, for example, with these Bunch-Davies type initial conditions and evaluate the wave function at early times, at late times, what you get is this plus stuff. There's a leading piece which is a semi-classical result, and this wave function then is approximated as e to the I as classical, and this piece can be now incorporated, can be used with what you would ordinarily do in ADS-CFT. Think of these things as sources for operators and so on, and then the dual CFT correlation functions for those dual operators works out like that. And using this dictionary, one can read off the energy momentum tensor 2-point function, for example, for appropriate graviton modes, and this then reveals a negative central charge, which suggests a ghost-like CFT. Okay, so if you do a
Go ahead after you complete. I have a comment.
So if you do the same sort of thing for other dimensions, what you end up with is a negative or imaginary central charge more generally. Okay, so Arrhenius, Hartmann, and Strominger proposed much later a concrete example of this for DS4. And they propose that the higher spin DS4 is dual to a symplectic Gauss CFT, a symplectic fermion Gauss CFT, a three-dimensional Euclidean CFT of symplectic fermions with SPN symmetry. This is basically an analytic continuation, amounted to an analytic continuation from the Klebanov-Polyakov ADS4 theory, okay, for the ON case. Okay. Yeah.
What you say was, you can extend this, and this is not the main emphasis in your talk today, but just to say, you can extend what Maldacena said for inflation, which is what his motivation was also. And that was sort of some of the work done here was along those lines. But there's a very interesting parallel between inflation and what we learned recently about ADS2, namely the breaking. In ADS2, what comes out of SYK is that the breaking of conformal invariance is important, but in a sense, the scalar, which is like the radius of the S2, evolves slowly. That's why you have a scale J, which is a big scale. And I just wonder, it might be worth going back to inflation, sort of, and thinking about it like that, a little bit with the new insights. Counting everything in terms of slightly broken conformal. There's no analog of the Schwarzian, but there might be some similar story. I don't know. It's just something that I feel now we should go back to.
That's an interesting thought.
But as you say, it is the scalar fluctuations are enhanced compared to the tensor fluctuations precisely because of this structure.
Yeah.
So maybe the scalar fluctuations are like the Schwarzian.
Yeah, exactly. That's exactly the thing to think about. And maybe we only looked at it so perturbatively that we didn't understand the full symmetry structure. Which is what the Schwarzian really buys you. And that would be really great. Anyway, I just thought
No, that's a good point. It's a good point.
You guys should work this out. I think it's a great.
That's an interesting point.
Okay. All right.
So this whole thing has to do with looking at the boundary, one boundary basically. But really, if you look at the bulk expectation values, the bulk expectation values really involve weighting the bulk operator, the bulk variables with the probability in the bulk, which is mod psi squared. And so if you look at the bulk expectation values, that what you would do is to evaluate a quantity like this, and this suggests that the fact that psi star and psi appear in these bulk expectation values suggests that the dual really involves two CFT copies. Okay. So this is part of the dictionary, but this is the other part of the dictionary, which is also important to study bulk objects. Okay, so somehow two CFT copies are involved, and in fact it will be quite clear how that enters in an important way in what follows. I should also say that in general this wave function is a function of the final three metric that you pick here, the final three metric on the final slice, and so one should really be, in terms of probabilities, also summing over all these final boundary conditions for bulk to calculate these bulk expectation values, and that is I think it's a difficult problem, and I don't have anything intelligent to say on this. Everything here is everything that's to follow is done assuming that the wave function is peaked around the flat metric, and then this I can then use this with one CFT copy.
What is the difficult problem again?
Well, so one is really summing over. One's really doing a probability in the bulk. So one is really weighting with the probability with mod psi squared with the wave function squared in the bulk to calculate these bulk expectation values. And the bulk expectation value, the wave function really is a functional of the final three metric also. So in general, the three metric also fluctuates, and so one should be having an additional integral over the final three metrics, over all final three metrics.
But at large n it's not so difficult.
At large n it's not so. So that's assuming that, yeah, exactly. So that's assuming that the final three metric is sort of is peaked on the flat case, and then that's what we are doing, and that's what I'm going to do in later. But this structure I think is probably important for something. For the full structure, and I don't know how to incorporate this at all. And so everything I'm going to say is going to assume that the final three metric, that the wave function is peaked around the flat metric. And
so I haven't understood. You're making a distinction between scalar and metric. That's what you're saying, is that metric is difficult while scalar.
I'm saying that if you were to think of these things as for example graviton fluctuations, right?
Yes.
Then this object, these bulk expectation values should be thought of as this object. But in addition, there should also be a path integral. There should also be an integral over the final metric, which is also one of the variables in the wave function.
Yeah. So you're making a distinction between the scalars and the metric. Metric is one of the fields in the bulk.
The metric is one of the fields in the bulk. Yeah, exactly.
Sure.
Yeah. And I'm just saying that, yeah. Yeah, you should have integrated all of them. Exactly, yeah. So it should not appear at the level of this and it doesn't appear at the level of what follows, I mean, at least. But I think the structure is there, and it is, I mean, so in some sense, it's really two CFT copies coupled to this low dimensional gravity, really, so to speak.
In a way, the wave function as a function of the metric is the most natural thing to compute. Because in Einstein gravity, that's all you can compute.
That's all, yeah, exactly.
Pure Einstein.
So, so I will not have much to say on this. I will basically assume that the wave function is peaked on the flat metric, and then looking and then this structure follows basically, and so on. Okay. So it's interesting to ask if all this of all that we've learned on entanglement, in particular the Rooth-Takanagi formulation and so on over the last 10 plus years, is something that one can think about in this de Sitter context. So just to put this in the context here, the Rooth-Takanagi, so the entanglement entropy is basically the entropy of a reduced density matrix of a subsystem, and it's given like this. One constructs the partial trace over the density matrix to construct a reduced density matrix, and then the entanglement entropy is the entropy of that reduced density matrix. So Rooth-Takanagi formulation basically says that if you construct a subsystem like that on a time slice, and look at all surfaces that bound the subsystem, and find those surfaces that have minimal area, those minimal area surfaces, and the area of those surfaces in Planck units is the entanglement entropy, and in some ways, and this is generalized for, this has a generalization for extremal surfaces for non-static situations and so on. Operationally, what one is doing is taking a constant time slice and looking at a boundary subsystem, and then the bulk slice on that corresponding to that, and then a codimension 2 extremal surface. Okay. So here the story is quite different. We are talking about a time-like boundary. We are talking about a spatial CFT really, and so on. And a speculative generalization of the Rooth-Takanagi formulation to de Sitter space might involve the analog, the bulk analog of setting up entanglement entropy in this dual CFT. What that might amount to is saying that one restricts to a boundary Euclidean, some boundary Euclidean time slice, which then leads to a corresponding bulk slice and codimension 2 surfaces in the bulk. And this might lead to a question of whether de Sitter entropy can be arrived at as some sort of entanglement entropy, some sort of generalized entanglement entropy. The de Sitter isometries would suggest that all such boundary Euclidean time slices are equivalent. There's no one particular Euclidean time slice that is sacrosanct. There's no time really. It's just a spatial thing. So whatever you use over here should exhibit the fact that all these boundary Euclidean time slices are equivalent.
I'm not understand. Sorry, what is a boundary Euclidean time slice?
So this is some spatial CFT.
Yeah.
And so I'm going to pick one of those isometric directions, one of the spatial directions there as Euclidean time. So I'm going to regard this Euclidean CFT as essentially an analytic continuation of some Lorentzian CFT, with that slice playing the role of the time slice basically.
So in Cartesian coordinate, I mean, just a space like just any slice, you mean?
Any slice for the time being, but what that amounts to is that in the bulk, something appropriate should happen in terms of looking at what sort of slices you can allow and what sort of slices you get.
And to be like an infinite slice.
Effectively, in the end.
And then you look at some region of that and ask
how entangled that'll be. But it'll become very clear in what I'm going to follow.
But just let me look at the analogy with suppose it had been space, a genuine CFT with time.
Yes.
Then you would take a region of space.
That's right, exactly.
But here, if I understand right,
I'm doing something similar. So I'm doing something very algorithmic similar.
Yeah.
What I'm doing is basically I start with this being the CFT. I regard one of these directions as Euclidean time,
yes,
boundary Euclidean time, and I then look at this slice and I look at some subsystem here, and I look at.
Fine.
That's the picture. Therefore, it's codimension 2.
Now.
Therefore, it's codimension 2. But there is no such meaning to taking this slice. This time this slice could have been anything, and it should have been anything. And the question is, how is that? So that should be part of the structure. So whatever I do, whatever slice I take, should not be sacrosanct, so to speak, and that will end up bearing out in what follows. So if this were to be fleshed out, then it should also be that this what this will amount to in the context of these ghost-like theories that appear in these DSCFT conjectures is that what one should be doing is to study entanglement entropy or the analog of an entanglement entropy in ghost-like theories. And then the question naturally would be is how is a positive definite quantity appearing from something like this? Okay, so that is the broad goal. So in general, what you would expect is that you get something negative in these kinds of things in ghost-like theories, and then what are the appropriate positive norm subsectors? That's what the goal would be.
Theory is not unitary.
It's not unitary.
So theory has nice properties of entanglement
Exactly. All of that are going to be up for a toss if you look at I think, and all that will end up bearing out if one just looks at one CFT copy. It turns out that anyway. So I'll get to that, and you'll see how that.
I really should wait to say this in the end for the later part of your talk, but there's a sort of similar issue which arises in gauge theories, because if you formulate a gauge theory, most generally you get ghosts, of course, and you can think about computing the entanglement in what we call the super extended Hilbert space, which includes all the ghost degrees of freedom as well, and ask, what is the answer you get, and does it agree with, say, the replica trick,
right,
and so on. And the answer is a little bit subtle, but the bottom line is the following. If you start with a state which is physical, that it satisfies the cohomology, etc., then the answer you get doesn't agree automatically with what you would have got in other situation, but it agrees with the replica trick up to boundary counter terms.
I see.
The replica trick answer has area law divergences,
right,
etc., etc. So if you define a suitably renormalized quantity, where you take away all the infinities, or you compute something like mutual information or relative entropy, which is independent of these divergences,
right,
then the answer doesn't depend on the details of the structure.
I see.
That is, as you change gauge fixing terms and their corresponding contributions from the ghosts, the physical answers don't change. So I'm just saying that's a kind of interesting story which I can tell you more about.
No, I would like to hear that. Actually, I did hear a little bit from Ronak, but yeah, but
ghosts,
right. So there's a whole separate direction there which we have been wanting to do, but we've not really looked at in great detail. But this, yeah. So anyway, there's some stuff that is here which I'll tell you. So this is the broad structure. So let me just tell you what happens if you look at if you just look at Rutakanagi in this context. So just to remind you, if you look at empty ADS, just ordinary Rutakanagi, the usual RT formulation. If you look at empty ADS, we're looking at a constant time slice, and this whole thing is a time slice, and we look at a subsystem here, and I'm looking at a strip-like subsystem for simplicity. And this is the area functional. You can extremize it, and you see that the surface naturally has a tendency to turn back. In other words, if this is the subsystem, for example, the surface goes in and then comes back out. So there's an optimization between the surface trying to go back and it's being able to lower area by going into ADS, and that's what the optimization is. And the deepest extent to which.
Sorry to interrupt. It is quite similar to what happens in ADS.
This is ADS. No, this is ADS.
Oh, this is ADS.
This is ADS. I'm just repeating ADS. In dCETA, it's completely different. That's why I'm just trying to point out differences between this and that. So this is ADS. In dCETA, if you set up the same sort of thing, I look at dCETA in the Poincare slice for the time being, and pick out one of these spatial directions as Euclidean time, and I look at this bulk Euclidean time slice, and I can set up an area function like this. And then I extremize, what you get is something like this, and there's notably a plus sign here in contrast with this minus sign here. So this plus sign is the thing that tells you that this structure is sort of different. It's quite different from ADS. The surface has no tendency to turn back. There's no real turning point. This sign difference from ADS is telling you that in dCETA, if you start off this surface here, it just keeps going on. And if you follow this through, you can show that you can artificially construct these entanglement regions by chopping these, by taking two of these half extremal surfaces and gluing them and so on and so forth. But there's no real turning point. That's the bottom line. Okay?
Can I ask you something? If I took the ADS formula and I continued R to I tau.
I'm going to get to that. That's exactly what this is.
Is it? But I couldn't get it because there is R to the 2D minus 2.
Yeah.
So that would give you minus I, or I to the 2D minus 2.
So what you need to do is, if you can just look at this, here I was implicitly taking b squared as positive, and if you instead take b squared to be negative, then what you find is that near the boundary, for example, you can see that what this amounts to is something like that. And if b squared is negative, then this surface really is like that. And this tells you that there really is an imaginary time path that you need to go down if you want to think of this the boundary direction as something real valued. And so this is an imaginary time path in DS4, which is a complex extremal surface. And if you follow this through, it turns out to be just the analytic continuation from the ADS Rutakanagi
There's no
expression.
dependence on that.
There is a redependence. So I'm not saying all that here. There is so this whole thing is for DS4, but there's something very similar that happens if you look at if the details change, but there's something similar that happens for general D also. These are complex surfaces and there's no canonical action, but it's consistent given that these are analytic continuations to define the area of these also to be the analytically continued answer. And that then amounts to something that gives you negative area in DS4. Okay. So this structure also turns out to be true for spherical surfaces, and it also agrees with the conformal anomaly and so on. And it's consistent with what you might imagine from one boundary, and the fact that this dictionary itself was an analytic continuation from ADS CFT, and so so it's not surprising. It's at least consistent that this whole structure is an analytic continuation from the ADS Ruta-Kanagi formulations. Okay.
So you get the same answer as an ADS CFT, including the same sign.
No, the sign is negative, so you get negative area. So in fact, if you looked at this answer for ADS4, what you got is this with R squared, and then R squared continues to minus R squared in DS, and that's what gives you this. So it's not clear how seriously one is supposed to take this because these are imaginary time paths, and you know, it's not clear what. But it's suggestive that this minus sign is what you might expect from a ghost-like theory also. But I'm going to pause here. I'm going to come back to that later.
When you say imaginary time path, I mean in de Sitter it is a proper surface, right?
It's not. These are not surfaces you can draw in de Sitter. That's the point.
In ADS it's a proper.
In ADS it's a proper surface. So these really are analytically continued from ADS. There is no such.
The extremization doesn't give a real.
It's not a real surface in.
X is, there is no solution to that equation d tau x. I mean, why not? I didn't understand.
If you look at there's no solution. So if you look at this thing, right? I mean, if you look at x dot squared, right? So this is you can see what happens here. So this firstly is less. There's always less than 1.
Yeah.
You see, there's no point at which it diverges, and it's that divergence that is required to make that surface turn around. So
there is some surface, right?
there's some surface. That surface is basically just a null surface in the limit.
Asymptotic.
It's asymptotically null.
But then, okay, then that's the answer.
That has 0 area.
That has 0 area.
That has 0 area. I mean, that has to have 0 area. In fact, that surface is basically just obtained by setting this to vanish. But there's another interesting answer in if you allow for more general boundary conditions. That's what I'm going to come to very soon.
But I mean, just to understand, if you literally just did things by the nose and tried to extremize, you get a null surface.
You get a null
0
surface.
Area. And then if you take the answer in ADS and continue, you get an x is imaginary.
You get a complex surface, yeah. You get a complex surface, and okay.
But wait, this null surface is for one boundary.
This surface is for one boundary, and
there's
so
the other boundary as well.
there's the other boundary. That's why
You get a cusp.
I get a cusp. You get a singular surface. So that's what you can. That's the best you can do, so to speak, with this. The other thing you can do, by the way, is to
Behind, what is one boundary number? You have some code.
no, just this boundary of this surface. I mean,
Imagine
just
that it's a strip.
so for example,
This guy, you get this thing that goes off.
so this is for example a strip.
Then they mean something.
Yeah. So this thing is a strip, for example, right? In ADS, these would join up like this. Here, what happens is that this thing starts off like that and goes like that. This thing might start off like that and either go like that, or you could take the other branch and it goes like this, and then this joins like this, and you can make it. You can make an artificial surface like this by gluing these.
I didn't just explain one thing to me. So you're starting, say, in de Sitter 4 with a 3-dimensional boundary.
Yes.
Then you're picking one direction and calling it time, so you're restricting yourself to 2D.
Yes.
And in that 2D, you're looking at some region.
Yes.
Right? That region you're looking at, in your case, doesn't have a connected boundary, is it? It has
a connected.
boundaries, huh?
Yeah, but it's a
Because you
strip.
looked at a strip.
It's a strip, for example.
Okay, now
You could look at spheres, then you get similar
now
structure and so on
I'm-
and so
now
forth.
I'm with you.
That's the idea.
In that case, you have this cusp. And what if it were a connected boundary?
It's the same. You still get what you get is
Yeah,
what you get is this. And if it's sufficiently symmetric, then of course it's just like a cone. I mean, it's a, but it's still that there is that cusp that remains, so to speak.
And can I ask you one more thing?
But there's one more thing that you can do here, which turns out to be that if you choose not these surfaces which go inward, but you could choose, for example, for a spherical surface, you could choose surfaces that go outward, and then you get this. This also turns out to be the case. Then there's again, these things just go off all the way. There's no turning point again. They go off all the way. So what you then get again is some area law divergence that those surfaces do exist, and I don't know what to make of them. But there is something very similar that I'm going to come to, or sort of with parallels that I'm going to come to very soon.
Rousseau has this generalized light sheet construction
Yeah.
or something, right? Which again sort of smells of null surfaces and so on. That, of course, I understand is different from your boundary, but in a sense, from the bulk point of view, that those would be kind of natural surfaces. Perhaps,
I don't know what to but I don't know what to anchor them on. I don't know what to anchor them on.
That's what
So
I
in
would rather
ADS,
they anchor on something
yeah.
nice.
So I don't know how to make sense of that in this context.
There is,
I mean,
if you were trying to think of some region on the boundary and holographically reconstruct it.
Yeah.
That is in the bulk or something.
Right.
Is that okay?
But I think that question will have bearing on what I'm going to say next, which is to look at the static patch or the static coordinatization. And there, this allows a global structure to desitter, and these are just the static coordinatization basically. And these are coordinates that allow the northern and southern diamonds to basically look very, very similar to the black hole-like region. And from these points of view, for observers in N and S, these lines then are event horizons, and T is just time, and translations then are symmetries in these patches. Okay. And now de Sitter entropy arises as the area of the cosmological horizon, and this was argued by Gibbons and Hawking long back, and you can work this out. And in the end, what appears is this object. Okay. And this is de Sitter entropy, and this is just the area of the cosmological horizon, and you can formulate it through the Euclidean formulation and so on. Okay. From the point of view of DSCFT, one could ask what happens to these future and past universes. Can you do something interesting with these boundaries? So the point is, if you look at a small patch here, that looks very much like the Poincare slicing. Okay. And you can see that is the case. But if you look at the whole thing, the global structure is like this, and then it leads to the natural question about whether there are extremal surfaces that go off like that, but not away, but they go off to the past boundary, for example. So we saw that there are no turning points like this that appear in the Poincare region. But if you now start off here, are there surfaces that go off like that, but go through here, and go up and go back and go all the way down to the past boundary? So in fact, in other words, I'm asking, are there boundary conditions that allow surfaces that use both future and past boundaries? Okay. So the answer is yes. That's why I'm telling you this now. And but to do that, it's useful to rewrite this whole thing in coordinates that are amenable to DSCFT. So in particular, I'm going to just flip this and call this tau as L over R and this W as the analog of time. And this tau is now
think of the past and future as the two CFTs.
As the two CFTs, but then
You want to think of entanglement
between them, yeah. But you know, just jumping ahead, the past CFT all sort of determines through bulk time evolution the future CFT. So in fact, what this really amounts to is two copies of the CFT at the future boundary. And then the question is whether there are entangled states between those. That's where this is in the end going. That structure, it turns out, dovetails with things that we found in the entanglement ghost systems and so on also. So anyway, I'll get to that. But this is what we're looking at, and this sort of also fits in with this observation that the bulk physics really requires psi star and psi, so two boundaries basically, and so on. So just to complete this, I start with this coordinatization. I write this in this.
Sorry, just to ask you, I mean, if you took this story of the Hartle-Hawking wave function and the path integral seriously, right? Then actually what the replica, what the full geometry computes is psi and psi star, because one boundary is bra and the other is ket, right? And then what you're supposed to do is glue, suppose you wanted to compute trace rho square, right? Is glue two such copies with the top glued to the bottom and the bottom glued to the top, right?
Yeah.
And in that sense, you are keeping track of both boundaries.
Yeah.
In a sense, right?
So
maybe
there's a lot of that actually, which I think fits into the story.
Okay.
But I don't think everything I don't think I've nailed everything down. But hold on to that one. So so here tau is really 1 over r. I mean, is L over r really, and so this is tau goes to 0 is the boundary here again, and then you can see that this is just like the Poincare slicing for small patches. So to jump ahead, if you can set up this extremal problem, it turns out, and there's some story here, but I'm going to just tell you the bottom lines. And if you look at again a boundary Euclidean time slice, the boundary Euclidean time slice here is either one of the equatorial plane slices or the W slice and so on. And I'm going to focus on the equatorial planes. All of them are equivalent because there's just rotational symmetry on this. You can now ask what happens if you set up the extremization like this, and then what you get is this structure here. And these are basically very similar to these Hartmann-Maldacena surfaces in the EDS black hole rotated. Okay.
Well, are you looking at real slices?
Now everything is real slices.
But between two boundaries?
Yeah.
And so therefore, just to understand, on both boundaries you choose a slice at constant Euclidean time.
Yeah.
Some region, and then you have a surface which goes from the boundary of that region to the boundary of the other region, extremizing the area.
Yes.
And what is the shape of that region?
This is, so this shape, so this thing is like a cylinder in some ways, right? And so
you choose a time slice and then you take out a region in that.
Yes.
What is the shape of that?
So this, yeah, that's the thing. So this thing, if you look at this, is a cylinder. If you take a slice there, it's again a cylinder. And this thing is so these surfaces for this for the sphere slices are roughly like this. They're something like this.
What was the freedom? You said that you were making some choice of particular boundary condition to do all this. What is the freedom?
There are all these rotational. There is the entire rotational symmetry here for the ST-1. There's also translations in W.
Yes.
And so those are all the isometries that are there over here. So I'm just using, so as far as this extremization is concerned, there's nothing more. I mean, I'm just setting up, I'm just looking at possible subsystems and.
But do you have some particular choices so the surface will go like this or not?
So the surface you can just set up and just ask what it does. And the extremization now tells you that what you get is an equation like this. Subject to this, the boundary subsystem being like this.
So if one asks the question that which surface minimizes the area, then the answer to this question
Is what I'm telling.
surface.
Is what I'm telling.
And there is no you talked about some boundary condition. There is no boundary condition in boundary.
I'm not sure what boundary condition.
Okay, so
I'm just saying that I start off with the subsystem here and a corresponding subsystem here, and I'm asking how. I'm asking for connected surfaces that go from here to there.
I actually still haven't understood. The intersection of your surface with either the past or the future is what shape?
This is the shape.
Shape meaning it's R times what?
It's R times S d minus 2.
R times.
So on the, suppose I'm doing, I am also a bit confused. Suppose I'm doing Desita 4, the boundary is R3, I choose an R2.
But then in the static patch coordinatization, it's really R cross S3. Oh, sorry, R cross S2. It's a three-dimensional boundary, no? So it's R cross S2 in this
It's R cross S2.
in the static patch written this way, in the static patch coordinatization written this way. Of that S2, I'm choosing some equatorial plane. So what remains is R cross S1, and that's what this is.
And you're choosing an interval in that R?
I'm choosing an interval in the R, and that's what this W is. And so those things are characterized by some width delta W, which is related then to the turning point that then exists.
And you choose the same interval at the top?
I'm choosing the same interval at the top and the bottom.
And the same S1, like equatorial S1?
Equatorial S1, yeah. But you could do this now, you could rotate that S1 and that whole thing works out, and that structure in spirit is very similar to a rotation of these Hartmann-Maldacena surfaces in the EDS black hole. Perhaps that's not so surprising because this structure, this coordinatization also is sort of like a rotation of the EDS black hole. I mean, by which I mean just flipping signs here. Okay. So it's not surprising that these surfaces are there, but they are kind of interesting.
So this rotates to the eternal black hole at a particular temperature?
Yeah. Well, not exactly, because these factors are slightly different. You see.
Yeah.
So it's not exactly. I'm saying it's similar in structure. That's why the detailed structure of the surfaces is not exactly that, I think.
But suppose I just rotate it.
Yeah.
What do I get in ADS if I just analytically continue?
You can't analytically continue. What this amounts to is if you switch these signs, if you flip these signs, then what was time here became space, and these surfaces then will become a rotated version of that. That's what I mean. These surfaces are like. Okay.
It's just, sorry, a remedial question. The static patch you get is not just, I mean, in higher ADS, in ADS4, the black hole is a different geometry from ADS, right?
Yes.
So, but your static patch is just part of de Sitter, right?
Yeah.
So your
It is all de Sitter. It's all of de Sitter. Yeah. This is well. This is
some, right?
well. I'm using these coordinates to characterize the future on the past universes. But you could continue this, and in fact, you really for drawing these surfaces, I really need the whole thing. So tau is not just restricted here in this range to just the future boundary, just the future patch where tau is less than 1, for example. Okay? In particular, if you restrict to that, there is again no turning point. If tau is less than 1, the turning point equation has no solutions, has no real solutions. So the solution, I mean, there are real solutions only if the surface is allowed to continue here, and it's in this region that the surface is turning around. You see?
So it doesn't lie entirely in the static patch, but somehow to characterize the surface on the boundary, you like to use the static patch.
Yeah.
But
And I'm also not using the static patch really. I'm using the future and past wedges, not the northern and southern diamonds. The static patch would have referred to these things, the northern and southern diamonds.
Okay. The analog of the Milne patches or whatever.
It's the Milne patches, if you like. Yeah, it's the analog of the Milne patches or whatever.
Okay,
Right,
fine.
exactly.
Well, also I was saying was that here the surfaces won't directly get related to the ADS black hole surfaces, right? Because
They don't. They're not directly related. They are analogous.
Yeah.
I think that's.
Okay.
I mean that's all. I don't think they are. I can't see any direct way
There was
to.
a statement that I vaguely remember that if you write down ADS black holes in an ADS slicing, then the Poincare patch is a black hole at a particular temperature.
Oh, yeah, this topology. Yeah, that's
Ah,
true.
I
That's
was
true.
wondering whether this was the analog of that.
Good one, good one. Good
Sorry,
one.
what is that statement again? I
Sounds like that. So that each slice is hyperbolic.
Yeah.
It's neither a sphere
Right,
nor
right,
plane,
right.
but
Yeah.
there's a third slicing. Which
Yeah.
is like, yeah, that's right. Then you get r square minus 1. You know, instead of r square plus 1 or r square as GRF.
I
Now,
see.
This could be, this sounds like it actually.
So then you could have your cake and eat it too.
Then it's
I
not
see.
quite ADS black hole, but just ADS sliced.
I see.
That sounds actually much like, I think that must be. I see.
So these surfaces have no turning point which lies within this wedge. This turning point is really there is a real turning point only inside here or there. And if you calculate the width of these things, it turns out that as this width grows all the way, asymptotically you can check that this is the relation between the width and the turning point. So in other words, these hourglass type thing basically tries to pinch off. Okay, and if you can now calculate the area of these objects in this limit where this is happening.
So in the case of DS3, these would be just GOD6,
In the case of GSC, they would be just GOD6.
and then null GOD6, or
They are not null because you see, if they were exactly null, then they would satisfy this vanishing, and they would again have 0 area. Then they would be exactly like these horizons, for example, at this. If they were other null GOD6, there would be these small wedges like that, for example. You see, so they're not really null. They're never null. They are really time-like.
trajectories of massive particles.
Yeah,
Something
they are like
coming
the
from
trajectories
past
of
and
yeah,
going
they are like the trajectories of massive
Now,
particles.
this is like a bubble coming from the past.
In some ways, yeah. In some
So
ways,
bubble.
yeah. In some ways, exactly. Yeah.
Okay.
So if you now look, let's just focus on DS4 now, and it turns out that you can show that the real turning point exists if B, this constant of this conserved quantity, lies in this range, and this is the only case where there are surfaces. So in other words, these surfaces basically tend to be repelled from this region. So you can only go so far inside over here, and now you can look at what the area of these surfaces is, and the area turns out to be this in this limit. Okay, in this limit where delta W goes to infinity, basically this turning point is basically arbitrarily close to 1, and what you get is something like this.
L square is the size on the boundary.
L is this the de Sitter scale basically, and this coefficient then, so what you get is just an area law type divergence.
You have a boundary of some. I mean, is there an analog of an area law divergence here?
It is like an area law divergence.
L square over G4 is like n squared.
Is like n squared.
And then where is the size of the boundary?
Yeah. So what you get is this quantity. You can now recast this in terms of the size of this boundary and so on. What you will get is some area law.
What would have been the size of the boundary?
The boundary, this size, yeah, I know. So this size here would have been, I think it's basically 2 pi L is what it would have been here.
So that L over epsilon C is like the area.
Is like the area law. If you write it in this way, this looks like this coefficient is precisely decent entropy, but it's an area law divergence, and it's not clear how significant, how sacrosanct this coefficient should, how seriously this coefficient should be taken. So
Well, your expectation was that you should get decent entropy if you took the interval to infinity?
yeah. Well, it's not an expectation; it was a question, and it's certainly scaling like that, but that scaling was expected because they were codimension 2. So if at all codimension 2 surfaces existed, then you should have automatically got out decent entropy. So that's not surprising. If the question is if they exist, and so in the Poincare slicing and so on, there was no such thing, but that's not even adapted to that. Here, this setup is adapted to that, and one should have got something like this if this bears out, and that is bearing out, and so that.
In some cases, wasn't your central charge negative and so on?
Yeah.
Here it is.
I'm going to come to all that. I'm going to come to all that very soon. I mean, okay, well, not very soon, but okay, infinite time, hopefully.
Just to get context, in the ADS situation, you could take all of space-time and still get a non-trivial entanglement entropy if there was a black hole. Right? You can have the surface that wraps around.
That's right. So in fact, that's actually partly what I was thinking in some ways here. So in some ways, these surfaces are sort of wrapping, I mean, almost like straddling this thing in this limit. You see, it's like this blue line, which is like the limit of this. But it's not quite like that, because these are not event horizons also. From the point of view of these future and past universes, they are not event horizons, they are Cauchy horizons, and it's a different structure. It's not the same.
But I mean, it does raise this interesting thing. You could take black holes in this.
Yeah. So then, in fact,
There's a story
the
there.
question is, if you look at a black hole and d-theta, Schwarzschild black hole and d-theta, and these things, for example, what you get is a structure like this. You get something like this, I think, and it's some pretty weird structure.
Yeah, right.
And it's some. And what I'm doing here is restricted to this thing. This is one de-Sitter, asymptotic de-Sitter patch, which is like that. So this thing raises the question of whether there are surfaces which do this, which do this, or which do this. You see? Multi-sheeted things, and so are there transitions between this sort of a thing and these? For sufficient, yeah, I don't know. There's some questions about how to set this up, and I think one can set it up, but I've not really spent time looking at this in detail. But I think there is something here to explore in greater detail here to understand. Yeah, but I'm going in a different direction now to see how this fits into DSCFT and so on, which is what the goal here was to begin with. So I was talking about SD-1 slices here, equatorial plane slices. You can set up the same thing for the doubly equatorial constant slices. They cannot be drawn on these on this thing. They're just a doubly equatorial constant slice is just a line here. It turns out that this is more tricky, but there are similar surfaces with the same area in the limit where you're looking at the whole space. Okay, but otherwise it's hard to find closed form expressions and so on. You get some complicated thing, but in general. But in this limit where you're looking at the whole space and so on, this is true. Okay, so that sort of bears out this, vindicates this statement that this Euclidean time slice was not really sacrosanct, at least at some level.
What was true in the limit that it was the whole space?
The surface that you get has the same. There are similar surfaces that go like this with the same area. Okay, so now. So I'm going to come back to this much later, but this was just the extremal surface story. The question now is how does this fit in with DSCFT and Go systems and so on and so forth?
Those are these different cuttings you said. The different surfaces of same area are the different ways of cutting the time slice.
Of cutting this, of defining a time slice,
Yes.
of defining a boundary Euclidean time slice.
Yes, boundary Euclidean time slice you could have chosen in random way.
Yeah.
These are
That's what this is. Yeah. So you could take any of these equatorial planes, or you could look at this W equal constant, whatever. But you get something. You get the same answer basically. That's what. Okay. So in the next few slides, I'm going to tell you about what happens here. And really, I'm not going historically. This whole structure I sort of arrived at by intuition from, by noticing some things here that Dilip and I had noticed and so on. So just to remind you, so in DS4 CFT3, what we have is a negative central charge and a ghost-like CFT, and this is sort of borne out by this Hartmann-Strominger concrete examples. you might think that there are negative norm states, and so that might lead to something like a negative entanglement of some sort. If that is the case, so firstly, is this true? And this turns out to be true. If that's the case, then where are the positive norm, positive entanglement subsectors, which you might think should be the case for an object like this? What are these things might in that context? Okay, so there's a long story in the replica formulation, which I'm not going to go into in great detail. But the bottom line turns out to be that you can set up the replica story for ghost-like systems, for ghost-like CFTs in particular, BC CFTs with C equal to -2, and more general CFTs, logarithmic CFTs with C equal to -2. There's a long story here. It turns out that the replica argument is applicable for the ground state if it is the SL2 vacuum. But in general, for the ghost-like systems, the SL2 vacuum is not the ghost ground state. There's a shift. For C equal to -2, it turns out that these two in fact do coincide. And so now these basic seeds do work. So to just to remind you of the replica argument, what we are doing is to start with some subsystem in some CFT, and we define a replica space where we take n copies of this and then glue them in an appropriate way and so on. And you can map that via conformal transformation to a single complex plane, and then impose the regularity condition, impose that that complex plane was basically the SL2 vacuum. And then you can read off the replica energy momentum tensor as from just the Schwarzian, and interpret that as a twist operator as something related to a twist operator 2-point function like this. Okay. So this whole thing makes sense only if the ghost ground state is the SL2 vacuum. For C equal to -2, it turns out that you can check that this is true. This regularity condition is trivial in general because there are ghost 0 modes, and you have to incorporate the background charge appropriately. But you can do that, it turns out, and then this condition has to be modified to something like this. And now there's a long story here. I'm not going to go into that. The replica formulation now formally applies, and then C negative translates to S negative. Okay, and the negative conformal dimensions that are required for this to happen, in fact, have been seen long back also, where by these people and others, where they were just studying orbifolds of the BC CFT and so on. Okay.
And then can you directly from a sort of state picture compute also the entanglement instead of that is why you have a
I'm going to
without positive.
Yeah, so I'm going to come to that. So that's why I'm not going to go into this in great detail, because it turns out that this is, there's some story here, but there are much simpler, much cleaner ways to see what's going on. And so if you want to abstract away, let's abstract away from these technicalities, these ghost CFTs and the replica subtleties and so on. We'd like simple quantum mechanical toy models of ghost-like systems with negative norm states, and that might then lead to a reduced density matrix after some partial trace and an entanglement and so on. So to do this, I basically cooked up something called a ghost spin. I don't know if this is there in the condensed matter literature. I couldn't find anything, but so an ordinary spin is something like this, where the up spin and the down spin have inner products like that. Up down is 0, but up is 1 and down is 1. So a generic state like this is always positive norm by construction. If we cook up a ghost spin, which is a 2-state spin variable with an indefinite norm, this is kind of abstract away from the BC CFT, from the B0 C0 algebra really. And you can actually find this in Polchinski in some sense, but not exactly this, but okay, it's very, very close to this. So define a 2-state spin variable with up and down states with these inner products. Okay, so these off-diagonal inner products. So up down is 1 and down up is 1. Now you can see that a generic state has a norm which is like that, and you can see that this is not positive definite in general. It's in particular, for example, up minus down has norm -2, and you can define a new basis of states, linear combinations which are manifestly positive and negative norm and so on. The question then is, if you look at 2 ghost spins, for example, define a reduced density matrix, trace over 1 ghost spin, you'll construct a reduced density matrix for the remaining ghost spin. What's its one-nominal entropy? What do you get, and so on. So there's a long story here, but the bottom line turns out to be that for even numbers of ghost spins, the calculations and interpretations are sensible. So in particular, let me just tell you what happens for 2 ghost spins in some detail. So I start off with a general state like this with 2 ghost spins. So this I and J are the labels for the 2 ghost spin variables. And so the state can be either plus minus, minus plus, minus minus, and so on. That's what these are. And so the norm is this, and you can see that these minus signs are basically where there's a single minus spin. Okay, so there are 2 contractions here with the inner product metric, and so there's a minus sign that arises only there's only one minus sign here. Okay, so for plus minus and minus plus states there's a minus sign, but otherwise these are positive. Okay. If one traces over the second ghost spin, for example, here, then the reduced entropy matrix has this form. And this is again very similar in structure to what happens for two ordinary spins, except that these minus signs signify what happens with these negative norm states. Okay. And the log of the density matrix can be defined using an expansion. And since you need to contract in correct ways and so on, it's useful to keep a mixed index reduced density matrix, which is like this. And then one can define the entanglement entropy like that. So in general, positive norm does not imply positive entanglement. Okay, it does not imply positive reduced density matrix or positive entanglement.
Of what?
Positive norm of the whole state.
Of the state for which you're computing the entanglement.
Yes. So I start with a positive norm state. If I look at ordinary systems, you get everything. Everything is positive definite. But if you look at a generic system like this, even if it's positive norm, you can break up the reduced density matrix in different ways, and these sublinear combinations can be whatever, and you get interesting things. Of course, you can arrange things so that there are subsectors where there are positive norm, where there's a correlation between positive norm and positive entanglement and so on, but that's not in general true.
And the
Okay.
density matrix is not a positive. I mean, I have to rethink it because the norms themselves are not, but at least it's a symmetric matrix, right? That's for sure. I mean, it's a Hermitian, Hermitian matrix.
Yeah.
So I can think of its eigenvalues, and they're not all positive.
They're not all positive, and in general, the entanglement is some, the eigenvalues are some complex things basically, and that's what this is. Now, of course, there are even.
So again, I'm sorry because the inner but are the eigenvalues at least real numbers?
No,
They can be complex.
they can be complex. In general, they can be complex. Of course, you can arrange subsectors where everything is nice and hunky-dory, and that in fact does happen. Of course, I'm going to tell you that very soon.
Then it's no longer Hermitian, right?
Yeah. I was just wondering what the inner. Yeah.
And the eigenvalue then it's
Yeah. So in fact, it's not in general that. Yeah. It's not even. Yeah. It's not even Hermitian. Sorry. No. Yeah. It's whatever this object is basically. Yeah. That's just a matter of taking this system and looking at its, looking at what that reduces matrix is and so on.
Entanglement entropy is not, I mean, you have to take log of some complex number.
Yes,
right?
you get
So
some.
you're not even sure what it means.
Yeah.
Like,
You have to choose
What these-
specific branch.
You have to choose specific branches and so on, and there are multiple branches here, and it's a complicated structure in general, and it's not clear this has to make sense, so to speak. It's what it is. It's sort of a natural formalism extension of what we ordinarily do in entanglement for ordinary theories, but it gives what it gives. So
Just one little cautionary note. For instance, BRST charges are Hermitian, and yet they're not diagonalizable.
yes.
Yeah.
So,
That's correct.
so the intuition, and that's because they're Hermitian in a fundamental. So the intuition that because something is Hermitian, it has to have real eigenvalues.
oh,
And that works if the norm.
I see.
So
Right.
that's why I was a
Yeah.
little
So it's not. Yeah.
cautious.
So okay, good. That's.
That's exactly why I was a little bit cautious.
So actually, I'm not sure now. Yeah. So about hermitity, I'm
But
not
I mean,
sure.
if you-
What I have done is to actually check you can check what the eigenvalues are, in
I
cases
mean,
and so on and so forth. That's
for you, if you wanted to compute rho log rho, you could do it by going to a basis which is where rho is diagonal, right?
yeah.
And you're just saying there the eigenvalues are not.
Are not, yeah. And of course, you can find. So even here, you can see that there are subspaces where everything is perfectly fine. So for example, there are what are called these correlated ghost spins, which I'm going to come to, and that is in fact what's going to play a central role later. And just to jump ahead, what that means is that if you restrict attention to just this subspace where you're entangling the same state from both copies, from both ghost spin copies, then everything is positive definite. Okay, so that you can see already here, but that's also something that's more generally true. But let me just look at a simple subfamily, which is a diagonal density matrix, and you can construct this subsystem. You can construct this subfamily where
Just for fun, in the two states system that Narayan invented, if you take the matrix 0, 1, 0, 0, sigma plus, that will be a Hermitian operator with his graph.
That's correct.
And it would look far from Hermitian. So all our intuition.
That's correct.
ah
That's correct. But that's true in Polchinski's example.
Yeah.
That's how it works. Yeah.
I see.
Yeah. But even so, I mean, linear algebra works, right?
Yeah, exactly.
If
Yeah.
you have a matrix which after a GLNR transformation you can diagonalize,
Right.
you can compute trace.
Right. Yeah. Absolutely. Yeah. Absolutely. So.
All right.
So.
Yeah, that's exactly the point.
Yeah.
So it's not Hermitian in the sense of writing up a matrices.
Yeah.
But if you do the correct inner product and you compute it,
Yeah.
then it is. This is exactly correct.
So in this simple subfamily, one can construct. You can see that positive norm correlates with positive entanglement, and negative norm correlates with all eigenvalues negative, and so in fact, what you end up with is a negative real part of entanglement and a constant imaginary part. What you get is something like this, basically. Okay. So this is this one parameter family where you can just look at a diagonal row A and explicitly just construct it, and this sort of thing you can do much more generally for arbitrary for higher Gaussian systems and so on also. Okay. So one can certainly find positive norm subsectors and so on here, which are perfectly in line. But in general, this is some general structure. Okay. Now, what could you find which are clearly uniformly positive norm? In general, if you look at, for example, the n Gaussian system, right, and you look at a state like this, where again I'm entangling the same state like this, right? You can see that the norm of the state becomes that. And this minus sign comes from this minus 1 to the n comes from whether from the n contractions that were there in this. There are n copies of this gammas that will appear here, and there'll be therefore a minus 1 to the n in this. Okay. So in general, you can see that for n odd, this structure is clearly not correlated with positive norm and positive entanglement and positive reduced density matrix and so on. But for even Gaussians, right, you can see that this is true. So this collection of states, for example, is positive norm and so on. So in particular, for example, for two Gaussians, you can see the analog of this state is this. So what I'm doing is entangling identical Gaussians from each copy. Okay, and this always ends up being positive norm and positive reduced density matrix and positive entanglement. Okay, so these are what I'm calling what we call correlated Gaussian states. And this is also true, it turns out, for two copies of Gaussian ensembles or Gaussian chains, which I'm going to come to very soon. So I'm saying you look at a general ensemble of Gaussians, and I construct two copies of those, and I entangle the same state from both copies. This turns out to be, you can show that in fact the minus signs always come in pairs, and so so they go away. Okay. And one can extend this structure. So this is already very suggestive, and so one can extend this to finite Gaussian chains with nearest neighbor interactions, and you can organize the entanglement and so on. You can also then show that for even Gaussians, the ground states are always positive norm and positive entanglement, and small negative norm doesn't change that structure. Okay. But what I want you to take away is this thing, that if you take two copies of this and entangle identical Gaussians from each copy, then what you get is something clearly positive norm, positive RDM, and positive entanglement. Okay. You can couple this to spins, and I'm not going to get into that. There's a long story here, but let's not go there. One could now ask, if I look at infinite Gaussian chains and I look at a continuum limit, do I get back a Gauss CFT, which is sort of the intuition that led me to this in the first place. And so this, in fact, Dilip and I showed that we can go here. So this would then suggest that Gaussians are perhaps to be regarded as microscopic building blocks of Gauss-like or non-unitary or more general non-unitary CFTs. And what we were trying to do was basically to go back to the Ising model of the critical point and look at the continuum limit and recover that and recall that this is really a CFT of free massless fermions and so on. So in particular, for example, let's look at a Gaussian chain with a Hamiltonian like that. There is nearest neighbor interactions, there's a hopping type interaction. So this sigma B's and sigma C's are operators like this. These are very similar to the BC operators of the BC CFT. This thing basically tells you that you kill an excitation here and you move it there, and so this excitation really hops, and so this is a hopping type interaction. And these are not so these operators are Hermitian, and they satisfy an algebra on the states like that, and they commute at neighboring sites. They anti-commute with each other here and so on. Okay, so they're a lot like the BC CFT operators, the B and C operators of the BC CFT, except that these are bosonic in the sense that they commute at distinct sites. So to construct something like a fermionic system, what we really want is fermionic analogs of these. So you can do that, it turns out, through what is a fairly standard thing. This is the Jordan-Wigner transformation, which starts here and goes to fermionic variables. And so This is not the same as what appears in the Ising model, for example, but it's an analog of that. And if you do this, there's some structure here. I'm not going to go into that. These things basically serve to precisely go away. I mean, take away the minus signs and so on. Precisely serve the purpose of doing this. So in the end, what you can do is you can show that these fermionic ghost-spin variables, in fact, satisfy an algebra like that. So in fact, they anti-commute at neighboring sites also, and they anti-commute like this. Now you can see that in fact you can just work through this, and there's a long song and dance, but you can work through this and show that this object basically becomes a lattice discretization of the BC CFT. Okay. And you can now take you can now use momentum variables and a continuum limit and so on. There's again some song and dance there, but in the end you can show that these appear to give you something like that, which is the usual, which is the known BC CFT algebra, which is not surprising because this already was a discretization of this. So there's of course a U1 symmetry, which is the fact that you can do phase rotations here, which is the analog of the U1 symmetry in the BC system. There's also a conformal symmetry. There's a global scaling symmetry like this, which is the analog of the conformal, which is what becomes a conformal symmetry in the continuum limit. Okay. So all this is for two-dimensional theories. I mean, they are effectively chains with time, and so they're really two-dimensional theories. We tried a lot to try to construct three-dimensional theories of this kind. I mean, starting with three-dimensional ghost spin chains and very similar nearest neighbor interactions and so on, and we just couldn't make it work. I mean, there are both technical things that we couldn't make work, like this Jordan-Wigner and so on, and also conceptual things and whatever, a collection of things that just don't fall in place. But there are many structures that are there, and it's quite suggestive. But okay, in the end, we haven't got there yet. So
there isn't any continuum formulation, known continuum formulation in 3 dimensions. Yeah, you were shooting for.
I was shooting for this thing exactly. In 3 dimensions, we know that there are these symplectic fermions.
Yeah,
So, for example, there are these known things, which is what Sartman-Strominger did. Huh? Polchinski's book doesn't talk about ghost versions of these things, but Lickler-Neubert, right, for example, which is what Sartman-Strominger used in this. It's just 3-dimensional symplectic fermions. For example, just this thing. Whatever. I mean, with some omega.
And just make them
these are anti-commuting, and this is a general version of this. Is general. This is what these are 3-dimensional symplectic fermions, and these are what end up. But I think there are more general things also. There are probably BC analogs of 3-dimensional analogs of BC type theories, which are probably topological. Okay, so the collection of things that we tried, we just didn't.
What is so what's the difficulty? If you start with this continuum thing, just discretize it. What goes wrong?
We couldn't manage to make this natural. So the natural interaction here is this. You see, this is the most natural thing that you can write down for these kinds of cosine variables and so on. And
so the Lagrangian level, just discretizing gives you the Lagrangian, right?
Actually, we couldn't even manage to make that work because, for example, here there are just at the level of mode counting already we couldn't see how this works. So if you're looking at this thing in 3 dimensions, you might think you need to have 3 of these sigmas and 3 of these 3 of sigmas b's and sigma c's and so on.
Suppose I'm just looking at Lagrangians.
Yes.
Going to Hamiltonians is another story.
Yeah.
At a Lagrangian level, I just discretize. I keep time continuous. I discretize
Right.
in space. I get some Lagrangian.
Yes, of course. Yeah.
Okay.
Yeah.
Now you may ask, what this is this integral over this Lagrangian is trace over minus beta h of what Hilbert space?
Yeah.
And that you say you have trouble answering.
I have trouble answering that in that language, but I also have trouble answering what operators, what spin-like variables I should use microscopically to consider that. If you just
the first question you
probably. But I recall having trouble even just with the mode the number of modes counting, and very basic things I couldn't end up right in my mind. But I probably have just missed something. I don't know.
Yeah.
So the normal course which appear, say, in a gauge theory, I'll have to go back and look. Some of the story certainly goes through. I can't. I guess the only issue is anti-commuting in adjacent sites nearby.
Yeah. So I don't think there's any question that there are ghost-like systems and so on. What I was trying to, the goal here is to try to find a.
Hilbert space construction.
I want a microscopic lattice model type construction which does this job.
No, even at the level of a microscopic discretized path integral, there's no problem. There's no issue.
Right. I don't think. Yeah. I don't think that is.
Asking about the Hilbert space. There are again site by site. Of course, on each site you can get everything to work. It's the adjacent site.
Right. Yeah.
which we have to.
Yeah.
I think it'll work. And
It-
we need
it-
to represent from.
It's quite possible that I've missed something very basic. That I think is a zeroth order statement.
No.
but-
I
but,
can't recall exactly.
But I also, to be fair, I also got tired at some point. Okay, so let's put that. So, but what you can now do is to ask if there are, n-level analogs of these kinds of things. Flavor generalizations, for example, things with internal structures. I mean, goes.
What I always find confusing here is how to read off the inner product from the Lagrange. That's always somehow I find confusing. But I can ask you.
I need to hear more of that. So here I've talked about two-state spin variables with things like this basically. Things like this basically. I want to now ask if there are analogs of this, generalizations of this with internal labels, with internal structures.
Like just to say, just in 2D BC system.
Yeah.
The inner product in the BC system is a sort of funny inner product.
It's this thing. It's this thing.
It's that one. Yeah.
It's that.
So how would we, knowing that I give you the Lagrangian, where do we tell? What is the algorithm that tells me that's the?
To go from the BC system to this, what you usually do is to look at the modes and look at the operators and look at what the algebra of the operators is, and then that is naturally consistent with this.
Some hermeticity is consistent with that.
Yeah. So if you stick in,
So
for example,
reality is consistent.
yeah. So if you stick in this algebra,
so
for example,
reality property is what forces you to do that.
it's some reality property.
Yeah.
It's basically saying that if you want this to work, this, if you sandwich between the up and down states, you can make this work out, and yeah, it's tied to reality and so on. Exactly.
It's saying that C is a real. I see. Thank you.
Yeah. So I want to now ask if there are these spin-like variables with internal structures. I mean, so in fact, it turns out you can do this. You can construct n-level generalizations of these co-spins where there are many ways to do this. It turns out. So here, for example, there's a O-n symmetry flavor generalization of this, where I attach internal labels with this. So this basically is n copies of the two-level go-spin system, and you can work through this and in great detail, and you can show that go-spin chains are criticality lead to BC CFTs with O-n flavor symmetry. So something like that. Okay. So this is a two-dimensional BC analog of this, where there are internal indices here. Okay. This will be the analog of the SPN in the symplectic fermion story. You can also construct symplectic n-level go-spins with symplectic-like structure in some ways, which has a flavor generalization like that, and the symplectic structure is built into this inner product, and this is sort of in part motivated by this three-dimensional CFT of symplectic fermions, and I'm not quite sure what the continuum limit amounts to here. It probably is related to these things, but we haven't gone that far. You can also do other things where you generalize these two states go spin to an n state go spin and so on. In all these, it turns out you can show that if you construct two copies of the go spin ensembles, then there are correlated go spin states where you entangle identical states between both copies, and then those always end up being positive normal positive entanglement. In addition, now if you also impose a restriction that you're only going to look at the ground state structure of this, then you can show that this has a dimensionality of 2 to the n, and in fact, if you impose additionally maximal entanglement, that these coefficients are all maximally entangled, I mean these reflect maximal entanglement, then you can show that the entanglement scales like n. Okay, and so now I'm going to go back to de Sitter and ask how this structure fits in, and what we saw was this structure. There are surfaces like this which straddle two copies and so on, and the existence of these surfaces suggests that perhaps DS4 is approximately dual to two copies of this CFT at the future and past boundary in a thermofield-double-like entangled state. Okay, and this is certainly consistent with what we've seen.
So this special combination it gave you positive.
Yeah, exactly.
Entanglement.
So I'm entangling the same state between both the future and past copies.
This is
And
in your example, special combination that gave you positive
yeah,
entanglement.
exactly. It's just these. I'm really entangling identical copies from both, and that's what I'm going to do here also. Okay, and this certainly So there are collection things that fall in place naturally. So firstly, Witten long back in his version argued that bulk time evolution basically maps any state here or any configuration here to a configuration here, and so this state is, you can show, is unitarily equivalent to a state like this, which has both copies entirely at the future boundary. So this is you can show that these are, you can use a bulk time evolution operator as a unitary operator and show that this is true. So one should really be talking about, one is really talking about two copies of the Gauss CFT at I plus in a thermofield-double-type entangled state. In these three-dimensional, so what I have in mind is that there are three-dimensional n-level Gauss spin chains in the universality class of these three-dimensional Gauss CFTs, and with n scaling like decent entropy.
But why are there two copies of the Hilbert space? If one is time related to the other, doesn't that mean there's only one copy?
There's one copy, but how do you construct a positive norm subset? That's the question.
No, but what does it mean to I mean, if you want entanglement of something with something else, they have to be direct products, Hilbert spaces, right? Or not?
By direct product, you mean?
H1 times H2.
Right.
I think.
Yeah.
Can I offer an analogy, which is how the thermofield double state arises usually in ADS CFT. That means you can take the state and time evolve it. If the full thermal circle is 2 pi, you evolve it by pi, right? Now that of course gives you the time evolved state, but now you take a tensor product of the original state with this state, and that gives you the thermofield double, you know, with this phase factor having become e to the minus beta pi over 2. So then of course it's two copies of the CFT, the thermofield double, right? And that's the representation of the double-sided black hole. So I have a feeling you're trying to do
I'm trying to do something very similar to that, because
take
that.
the time evolution, but then you take the initial state and say that's also part of a final setup for a product of two conformal field theories.
Right.
What confuses me is you can't change what's happening in the past without changing what's happening in the future.
True.
Unlike the two-sided black hole,
Yeah.
you can send in stuff here, not
Yeah.
send in stuff.
True.
So I mean, I don't.
But this is, yeah, sorry, you're right, But you can think of this as some particular state in the two conformal field theory system, you know?
Yeah. So these are only certain subsectors in the two
So
copy
you're saying,
system.
consider an auxiliary Hilbert space with two conformal field theories, and then look at the subset.
Look at the subset which is
where one guy is time evolved with the other.
yeah. That's effectively what it amounts to, basically. So it's
I
not,
think
it's
that's
not,
what
they're
we're
not,
doing.
yeah, that's
We
what
don't
effectively
want
I'm,
to focus on this
on that, yeah, that's, because that's the only interpretation I can provide to this from the point of view of a dual with, where I knew what those structures were and so on. I mean, where only, you can only do so much to get something positive norm and so on. And so, if you in particular look at three-dimensional n-level Gauss spin chains in this universality class of this, then you can, with n scaling like the entropy, then you can show that these two copies of this in fact is positive norm and positive entanglement and so on. And so near the boundaries, what we really have are two Euclidean, is a structure like that, and so this is a Euclidean CFT on R cross SD minus 1. And so in particular for DS4, it's really R cross S3. And so this global structure really is, global de Sitter is really dual to two copies of the CFT on this space. So if the entropy comes out like that, at least at the level of scaling and so on, where is the temperature coming from? Is it related to the Casimir energy of the Gauss CFT on this cylindrical space? This Casimir energy will certainly scale like 1 over L, 1 over the size of this. That's what I'm hoping, but I don't know how to make this more precise at this point. Yeah, I'm basically done. So let me just stop here and.
No, I'm sorry, but go ahead.
So if one were to look at this, what one is naturally led to ask is whether there's a more, whether a clearer formulation for a replica for Z star times Z, for example. there are these horizons and these surfaces seem to go like that, and it naturally is to ask if there's an analog of a bulk reconstruction, and what are these states which are here? Are these two CFT copies supposed to know this? Are they the analogs of these mirror operators? Whatever. I mean, so let me just stop here. So I think this is a collection of things which.
I have a question. So there's some interpretation of the DS entanglement entropy in terms of the Hartley-Hawking state at some time slice and then tracing out over. I mean, if we have some quantum gravity in DS, then tracing out over the left wedge. How does your picture relate with that?
Yeah, so I think one has to probably address these questions. I mean, how does one encode these regions in this and so on? And it's not clear to me. I mean, that's the short answer.
And what do you mean by the worldsheet entanglement?
Yeah, so
Do you have some particular
I have something
ingredient?
I have something, no, not in this context at all, but these ghost pins
I see, okay.
have a life of their own, and so you could ask,
I see.
what I had for the replica, for example, was that there is something like, I mean, these ghost-like theories for at least for these states give you negative entanglement, and you could now ask if you construct a worldsheet theory with ghosts. That's not been done. I've not done that for 3 to minus 26, but if one could do the analog of that in that case, probably it will not be as simple as this. There will be more there. But if that's the case, then is there some analog of how space-time entanglement dovetails with worldsheet entanglement? And there's been some thoughts along these lines in some papers I've noticed, but that's the. But that's far away. I don't really know how to.
Yeah, I'll make a vague, probably pointless statement, but anyway, in this Papadodimas Raju construction, there's only one side, one Hilbert space, but there's some effective sense in which there are almost two.
Yeah.
And there are the single trace operators on the left, the simple operators on the left, and the simple operators on the right, and they're almost independent of each other. So that is one context in which there may be some precise sense in which you can compute the entanglement of some built out of the algebra of some simple operators here and some simple operators here, even though there's no real separation of the Hilbert space. That's one context in which I know, in which it seems reasonable, where you don't have two Hilbert spaces, but there may be some entanglement questions for which we pretend there are two. Do you know so let me ask you, do you know if anyone's done entanglement entropy constructions of the sort I'm talking about from their construction? Computations. Is that possible? If I compute the entanglement entropy of something in a two-sided black hole, something here and something here, that's a well-defined question. It's given by some surface of some state.
Yes.
Some surface of some minimal surface. Now, can one, in the Papadodimas Raju sense, try to mimic up that calculation somehow and see where it starts failing?
I'm wondering if they have themselves, if Subrat in particular in some of these recent things has
done this?
Well, may not have done this exactly, but has set up something which. But even outside of that seems like the only context where I would have imagined them doing this. But there have been studies of this kind of entanglement in this context and so on. In particular, this Schenker-Stanford paper themselves, right? What they were trying to argue for with this connected surface like that, if you remember the shockwave thing. They were setting up.
Genuinely had two different.
Yes, exactly. Yeah, exactly.
But here there's this sort of interesting question, right? I mean, you've got two almost algebras.
Yeah, yeah.
They're not quite algebras.
They're not quite. Yeah, exactly. Yeah. It's actually very similar to that. Exactly. Yeah. But I can't recall anything that people have done in this in that context, and that would have been the simpler thing to do than this.
Okay. Yeah.
I mean, there are many more complications here which.
Yeah.
which
Yeah. Okay.
but I should look. I mean, I should check if
It may be out of control, but that's not. If one can compute.
No, but even toy models, right? I mean, you may not need to do the whole thing, but finite toy models are.
Far away. These two things are sort of far away. The problem is that they are not algebras by itself. You are
Yeah.
saying, right? But in this example, they are at least they are far away. I just make comment.
Yeah. So I think for this to become interesting, what will have to happen is that something simple here, after time evolution becomes complex.
Mhm.
If something simple here remains simple here, then you can artificially do it, but there's no real separation between
This and that,
here.
yeah, exactly, yeah. So
But if dynamics is complicated enough, so something simple here translates into something very complicated. Then the entanglement between the simple degrees of freedom here and the simple degrees of freedom there may be an almost well-defined question. That will depend on dynamics and various things. Whereas in the Spapaverdi mass, Raju think that's exactly what their idea is.
right,
That something that is simple on the left Hilbert space is something very complicated.
very complicated, right? Yeah.
I wonder if that is a context, they must have thought of it, but I wonder if there's a context in which one can actually do a calculation with this.
I should look at that anyway, certainly. I think.
It's probably me.
No, but